Welcome to day 2 of transformations. We're talking about reflections today. Reflections always make me think of an art project I did when I was little, where I would paint on one side of a piece of paper, and then while it was still wet, fold it over and see what shows up on the other side. And it was just a mirror image, like a reflection, a flip. So I'm going to recreate that for you. I didn't have any paint, so I'm going to use glue. I'm going to do sort of a cinnamon roll type swirl, maybe. And fold it over for a reflection. Oh, beautiful. Beautiful. So what you get is a congruent image. Are you thinking the word I'm thinking? Congruent image, isometry, and it's reversed, but it's congruent. It has sort of a different orientation, just like when you look in the mirror you see a reversed image, but you can see that this spacing is the same. Just got glue on my hand. The spacing is the same. Yeah, that's what I think of when I think of reflections. If you would grab your little note sheet, we're gonna just try some on a graph. I think that's probably the easiest way to do them, because then you don't have to break out a ruler and measure from that fold line. I'm going to do mine on paper too. I just think it's easier that way. So the first thing to know is, where are you going to fold the paper? And so let's start with, each one has a different fold line, so let's just draw in the fold line. On number 1, we're going to use the x-axis as our folding line, so maybe just trace that out so you remember that. The second one we're going to fold on the y-axis. The third one, I want to think of all the points that have x values of -1. So that would be all the points back here, all the points up here have x values of -1. It's actually a vertical line. Number 4, y values of 1 are all right up here. Number 5, when the y value is opposite the x value, or you could think of that as a y equals mx plus b, a slope of -1. But the y values are opposite, so like if x is 3, y is -3, 2, -2. So it's going to be perfectly 45-degree angle, negative sloping line. And number 6, when the y value equals the x value, 1 equals 1, 2 equals 2, 3 equals 3. If you're thinking mx plus b, that's a slope of 1, a y-intercept of 0. So there's our fold lines. So let's go back in and see what our reflection would look like. So on number 1, imagine you're folding over the x-axis. You could honestly do it if you wanted to, if that would help. But if we folded right here, this A point up here, the image would show up 2 units below the line. So let's call that A prime. This point C from the pre-image would fold over and wind up at C prime. And B folding over, it's 4 units up, winds up 4 units down at B prime. And so we get a congruent triangle that's just sort of flipped, it's reversed. For number 2, a y-axis. Be a little careful here because those letters are important, because the D flipped over at D prime. And the A, which is 4 units away, so 4 units away, you should see the A prime wind up on the right side of D prime. So that's just why I said be careful with your labeling. C prime right here, B prime 4 units away, so B prime. Congruent little rectangle there. Alright, let's get into a challenging one. Number 3. So can you imagine if you got paint on both sides of the line, how that would work? It's kind of like this little triangle here would reflect over on this side, and this chunk right here reflects over here. So you could go point by point. This A point folded over this line is going to wind up 2 units on the other side of the line. So ignore the axis. This is this line is our fold line. So here's A prime. B prime is going to work the same way. It's going to be 2 units away from the line. So 2 units on the other side. And then C prime, if we flip it over this line, is going to wind up on the left side of the line, 1 unit away. So this one maybe feels a little awkward because the image actually overlaps the pre-image. Number 4, another overlapping one, right? So anything that was, if we're folding over this line, anything below lines up above. Anything above, if you fold it over that line, winds up below. You have to really pay attention to which line you're using, right? Maybe make it a different color like I did. And this is always the ultimate test when you draw your image. Is it congruent? You'll know if you mess something up, it won't look right. Okay, these slanted lines are sometimes more challenging. Sometimes I like to turn my paper just so I can sort of visualize this. So here's my fold line, straight up and down. So I want the A to go straight across that fold. So it's almost like, can you see how it's going to fold at sort of a 90-degree angle there? So if it's one diagonal from the line, it's going to be one diagonal on the other side. Okay, this one, the B. Again, you have to go straight to the line, so you want to go kind of an up one, over one, rise over run. So it's 2 perfect diagonals from the line, so we're going to go 2 diagonals on the other side. What do you do with the point that's on the line? What if you got paint right in the crack of the fold? It just would stay there. So D prime is right where D is, and C prime is right where C is. And so if we connect those, that horizontal line becomes vertical. And there's our mirror image. Same thing for number 6. We're going to, again, I like to turn my paper. It helps me see it better. So if this is straight up and down, that C is going to be 1 diagonal and a half from the line, straight to the line. And so half and 1 diagonal from the line, put C prime right on the y-axis. A here was 1 diagonal from the line, so there's A prime. And B, let's see if we can do this. 1 diagonal, 2 diagonal, 3 diagonal. 1, 2, 3. There's our isometry. We see congruent triangles folded across that line. Lovely. All right. Flip that paper over. We've got some interesting facts about reflections. The reflected image is congruent to the pre-image. We call that an isometry. Write that down. Isometry. While a translation requires a direction and a distance, like that vector arrow, a reflection just requires like a fold, get out of here, a fold line, right? You just fold that over, so just a line. That's all you need. Okay, this one might be a little confusing, so let's think about Birdie's wing as point P. And when we reflect it over that line, there's the image, P prime. And this is talking about the actual line segment that connects P to P prime. Alright, so what's special about the line of reflection and this line right here, this segment right here? Well, they were supposed to be equal distance, so that would make this a midpoint right here. And on top of that, this should be a nice 90-degree angle if you're folding it correctly, right? And so we wind up with this line going right through the midpoint at a 90-degree angle. We call that perpendicular, and at the midpoint, bisector. The perpendicular bisector. Fantastic. Working at the mall. Here's Herberger's. Here's Orange Julius. Employees have to park far enough back in the parking lot so they don't take up important customer spaces. So there's this line where they're allowed to park behind this line. If you're lazy, you're going to park right on that line. If I want to park really close to Herberger's, I'd park right here. If I want to park as close to Orange Julius as I could, I might park right here. If I want to make a trip both to Herberger's, to my car, and then Orange Julius, I might park somewhere in the middle. If I parked way over here, I'd get way too much exercise. But somewhere in the middle. So if I were really lazy, I'd calculate where's the perfect place to park so I don't have to walk very far. So if Orange Julius was on the other side of the street, think of a reflection. That looked like a reflected Orange Julius on the other side of the street. I know exactly where I'd park. The shortest distance would be a straight line. I would park right there. Right there. So if that's the shortest distance for across the street Orange Julius, isn't this distance going to be the same as that? So really, this would be the perfect place to park, even for this side of the street Orange Julius. So that's a theorem in our book, but it makes sense. If you just think of the reflection, then you're going to maximize efficiency by finding that intersection point to park at. All right, last thing. Oh, not last thing. So we are going to reflect AB